Ever looked at one of those really complex circuit diagrams, maybe the guts of an old 741 op amp or, some cutting-edge CMOS
Oh,
design,
yeah.
and you just think, how? How does all this work? It's pretty clear that the stuff from, like, your basic electronics 1 course, while it's crucial,
Absolutely. Foundation.
it just scratches the surface for these kinds of designs.
You're totally right. Those early concepts, they give you the building blocks. But modern circuits, well, they combine them in some really ingenious ways to get performance far beyond what just one component can do.
Okay, let's unpack this.
Yeah.
Today, we're taking a deep dive into one of those foundational, but kind of advanced circuit topologies. It really bridges that gap, the cascode.
The cascode, yes.
Our mission really is to pull back the curtain on why it's so fundamental. First as this super efficient current source, and then maybe even more importantly as a powerful amplifier.
And get ready for some serious aha moments, I think. We're going to try and pull out the most important nuggets from this detailed university lecture material you shared.
Yeah, think of this as your shortcut. To understanding the clever design choices behind everything from your phone to, like, complex medical devices, hopefully with a few surprising facts, maybe keep you hooked.
That material, especially Professor Razavi's Electronics II lectures, it really provides an incredible blueprint.
It does. So let's jump right in. Let's talk about the why. Why the cascode? What problems does it actually solve?
Okay. To really get the cascode, we kind of need to go back to the idea of an ideal current source first.
Right, the textbook version.
Exactly. This, theoretical device, it gives you a perfectly constant current, doesn't matter what voltage is across it.
Perfectly flat IV curve. Infinite output resistance.
Perfect. Infinite resistance, which, of course,
You can't buy one.
you can't go buy one, no. So engineers try to build them. And a simple way is using a single MOS transistor, right, in saturation. It tries to act like one.
Tries its best. But it's not perfect, right?
Yep.
What are the main limitations?
Well, the big one is something called channel length modulation. It basically means the current isn't perfectly flat. It slopes up a bit with voltage.
So not infinite output resistance. It has some finite value.
Exactly that, Ro. And the other big limitation is its voltage range, if the voltage across it drops too low.
Like below VGIS minus VD.
Precisely. Below gate voltage minus the threshold voltage, if it drops below that, poof, it leaves saturation, goes into the triode region.
And then it's not acting like a current source at all.
Not a good one, no. Its
Yeah.
behavior changes completely.
Okay, so current isn't perfectly constant limited voltage range. I remember from, Electronics 1, a common trick was adding a resistor, a degenerating resistor, RS, at the source.
Right, resistive degeneration.
What does that actually do for us?
It helps. It does increase the output resistance quite a bit.
Yeah.
The factor is roughly 1 plus E-MERO.
Where GM-Rout is the intrinsic gain.
Yep, the transistor's intrinsic gain, usually, somewhere between 5 and 10, maybe a bit more.
Yeah.
So you get a decent boost in output resistance, makes the current flatter.
Okay, sounds good. Better output resistance. But electronics, there's always a trade-off, isn't there? What's the catch here?
Absolutely. There's always a catch. And here's where it gets really interesting. That improvement, it costs you voltage range. Big time.
Oh.
With lowest voltage the transistor can handle before it drops out of saturation, it moves up. It increases by the voltage drop across that new resistor, RS.
Which is ID times RS.
Exactly, IDRS. So you need more voltage headroom just to keep it working as a current source.
So we made the current flatter, but shrunk the window where it actually works. We sacrificed voltage range.
That's the trade-off.
Right. So this really begs the question, can we get that high output resistance without killing the voltage range? Is there a better way?
Precisely. And this is where the Cascode provides that aha moment.
Right.
Instead of using a resistor for degeneration, what if we use another transistor? Let's call it M2. Put it in series with the original transistor, M1.
Another transistor.
Okay.
So M1 is still trying to be the current source, and M2 is sitting on top of it.
Kinda, yeah. M2 is doing the degenerating job that the resistor did. But here's the key insight. A transistor in saturation, unlike a resistor, doesn't just follow Ohm's law.
Right.
The voltage it needs across it, its drain to source voltage to stay in saturation, well, it can be pretty low
Yeah.
and fairly constant.
So it doesn't demand as much voltage headroom as the resistor did for the same effect.
Exactly. It's a much better degenerating device if you care about voltage range. And the output resistance boost is fantastic.
How good are we talking?
For this cascode current source, the output resistance is approximately Well, it's the output resistance of M2 row 2 multiplied by the intrinsic gain of M1, GM1 row 1.
Wait, so it's GM1 row 1, row 2.
That's the one.
Wow, okay. So you take the already decent output resistance of M2 and you multiply it by the entire intrinsic gain of M1, if that gain is 10.
You get a 10x increase overall compared to just M2 alone. Much, much flatter. Much closer to ideal.
That's a huge improvement. Okay, so what are the rules for making this work?
Two key things. First, both transistors, M1 and M2, they absolutely must be in saturation.
Okay, both saturated, got it.
Second, the connections. The source of the top device, the cascoding one, M2, it has to connect to the drain of the bottom one, M1.
Source of M2 to drain of M1.
Right.
And this isn't just for N-type transistors, is it? You mentioned P-type cascodes, too.
Yeah, absolutely. The principle is identical for P-type devices like PMOS transistors or PNP bipolars.
So they draw current from the positive supply VDD down to a node.
Right, instead of from the node down to ground like N-types.
Yeah.
But the cascode idea, stacking them up, boosting output resistance, it works exactly the same way.
The small signal models, the equations for output resistance, they're analogous.
Completely analogous, just, mirrored voltage polarities. Same benefits.
Okay, so cascodes are brilliant for making better current sources. Huge output resistance, decent voltage range.
Yeah.
But amplifiers, that's where we really want big gains, right?
Yeah.
Basic amps, like a common source, their gain is often pretty limited, like maybe GM-Rout 10, 20, something like that.
Yeah, often in that ballpark. And for many applications, that's just not enough. We need more gain.
So how do we get there? You mentioned a powerful way to think about gain calculation.
Ah, yes. This is a really useful perspective. For basically any linear circuit, you can find the voltage gain, AV, in two steps.
Right.
Step 1. Find the overall transconductance. We call it capital GM. You find it by shorting the output to ground and figuring out how much output current you get for a certain input voltage. So GM is out VIN with VOUT shorted.
All right, find the overall GM. Step 2.
Step 2. Find the overall output resistance. Capital Rout. You do this by setting all the independent input sources to 0 voltage sources become shorts, current sources become opens, and then you look into the output terminal and measure the resistance you see there.
Okay, find GM, find Rout, then what?
Then the magic happens. The voltage gain is just AV equals dash GM-Rout.
Simple as that.
Yeah.
AV equals dash GM-Rout.
Simple as that. And the beauty is if you want more gain, you just need to increase GM or increase Rout, or both.
Okay, I see where this is going. We just spent all this time talking about how cascodes give you a huge route.
Exactly. So what if we use that cascode structure in an amplifier?
Right. Let's take an N-type cascode. M2 gets the input signal. M1 is the cascode device on top. What's the overall GM?
Well, it turns out the overall transconductance, the capital GM, for that configuration is pretty much just the GM of the input transistor, GM2.
So don't lose much GM.
Not really, no, which is great.
And the route?
The route is precisely that super high cascode output resistance we just calculated, that GM1, row 2 thing.
So the gain, A equals Dan's GM-Rout, becomes roughly Nevis GM2 times. GM1, row 1, row 2.
You got it. It's approximately the product of 2 intrinsic gains.
Wow. That's not just a little bit more gain. That could be huge. Like hundreds, even thousands.
Potentially, yes, in a single stage. This is why cascodes are so powerful for amplification. It really moves the needle on what's possible for, sensor precision, signal clarity.
Okay, but an amplifier needs a load, right? To turn that current into an output voltage, what kind of load do we use?
Good point. If you just use a plain old resistor as the load, well, its resistance is probably way lower than the cascode's route.
So the resistor dominates the parallel combination and the overall route tanks.
Exactly. You lose all that beautiful high output resistance you just created. Your gain drops dramatically.
Okay, so no simple resistor. What about using a simple current source as a load, like a single transistor?
Better. A single transistor current source load has an output resistance of ρ. That's better than a resistor, but still. It's probably much lower than the cascode's output resistance. It will still limit your gain significantly.
So if we want the maximum possible gain, we need a load with a really high resistance too.
Bingo. And what structure gives us really high resistance?
The other cascode.
Precisely. The optimal solution is to use a P-type cascode current source as the load. Usually PMOS transistors, say M3 and M4, stacked up.
Okay, wait, so the amplifier stage itself is an N-type cascode looking down.
Right.
And the load is a P-type cascode looking up.
Exactly. You've got a cascode pulling down and a cascode pulling up.
And the overall output resistance route is the N cascode's high resistance in parallel with the P cascode's high resistance.
That's it. Two very high resistances in parallel. That gives you the highest possible overall route for the stage.
And that combination, the cascode amplifier with the cascode load, gives the maximum single-stage voltage gain.
That's the bottom line. This cascode with cascode load structure is how you squeeze the most gain out. We're talking gains often in the range of, say, 50 to 300, maybe even more.
That's a massive improvement over the 10 or 20 we started with. Huge leap.
It really is. And just to mention, the same ideas apply if you build this with bipolar transistors. You just need to remember things like or P in the bipolar small signal model.
Right, the base resistance equivalent. Okay,
Yeah.
Let's talk tuning. How can we tweak this? Say, what happens if you reduce the bias current ID going through all the transistors in that cascode amplifier, cut it in half?
Okay, interesting question. You might think less current, maybe less gain.
Yeah, intuitively.
But think about the components. The transconductances, the GMs, they depend on the square root of ID, so they go down by root 2.
Okay.
But the output resistances, the rows, they are inversely proportional to ID. So if you have the current, the rows double.
Oh. So GM drops a bit, but rho doubles. What does that do to the overall gain-aided GM-Rout?
Since the gain depends on products like GM-Rout, the doubling of the rows dominates the slight drop in GMs. The overall voltage gain actually doubles.
Wow. Okay. Less power, more gain. That seems like a win-win.
It is, in terms of gain per unit power.
Meh.
Now, what about transistor size? What if you double the width, W, of all the transistors, but keep the bias current the same?
Wider transistors,
Mm-hmm.
more current capability, so GM should go up.
Right. GM depends on the square root of W, so GM increases by root 2.
And rho, how does that depend on W?
It doesn't directly. Rho depends mostly on channel length and bias current, so rows stay pretty much the same.
Okay, so GM goes up by root 2, rho stay the same. What happens in the gain, that GM-Rout?
Again, because gain involves products of gems and rows, that increase in gem by root 2 means the overall voltage gain also doubles.
Interesting. So you have these like knobs you can turn. Bias current affects power and gain.
Yeah.
Transistor width affects area and gain.
Exactly. Powerful design levers. Lower power can mean higher gain. Bigger area can mean higher gain. Trade-offs. Always trade-offs.
Now, this raises an important point. You mentioned connecting the input to M2, the bottom transistor. What if you mess up? What if you accidentally apply the input signal to the gate of the top cascode device, M1, the bad cascode?
The bad cascode. Yeah, that's a really instructive mistake to analyze.
What happens then?
Well, the output resistance looking into the drain of M1,
Yeah.
it doesn't really change. It's still that high cascode resistance looking down.
Okay, route is still high. What about GM, the overall transconductance?
That's where the problem is. The overall GM just plummets. It drops drastically.
Okay.
Because that top device, M1, now sees the entire resistance of the bottom device, M2, roughly 1 G-2 plus rho 2, acting as degeneration in its source path. It becomes heavily degenerated.
So it struggles to convert its input voltage into an output current.
Terribly. Its effective transconductance gets killed. So the voltage gain from the gate of that top cascode device to the output ends up being very, very low.
A real warning sign. It shows why putting the input on the bottom device is so critical for getting that high gain.
Absolutely emphasizes why the standard configuration is the way it is.
Okay. And just like we can have N-type or P-type common source amps, can we build a cascode amplifier with a P-type input device too?
Oh, definitely. You can absolutely have a PMOS input transistor cascode connected with another KMOS. The whole structure can be flipped.
And the gain principle still holds. AV equals dash GM-Rout.
The fundamental relationship is always there. The route structure would still be that high impedance cascode looking up, probably loaded by a high impedance N-type cascode looking down.
But the overall GM would now be set by the transconductance of that P-type input transistor.
Exactly. The GM of your PMOS input device would determine the capital GM. The principle holds perfectly.
You know, this whole discussion, it really drives home how powerful that GM-Rout way of thinking is.
It really is.
It lets you look at these complex circuits, multiple transistors stacked up, and quickly get a handle on the gain without drawing pages of small signal models.
It gives you incredible intuition. You start seeing the building blocks, the high impedance cascodes, the input transconductance stage, and you can estimate the performance almost by inspection.
So what does this all mean, really? We've gone pretty deep into the cascode here.
We've seen its elegance, its power, how it starts as a clever way to fix current sources and then becomes this amazing tool for building amplifiers with truly impressive gain, all in one stage.
And it's kind of amazing that these ideas developed decades ago are still so central to how we design high-performance electronics today.
It's a testament to really solid engineering fundamentals.
So understanding the cascode means, when you look at a complex schematic, you're not just seeing a mess of transistors anymore.
Hopefully not.
You're seeing deliberate design choices, balancing output resistance, transconductance, voltage range, all to hit specific performance targets.
Exactly. You see the intent behind the structure.
Okay, so here's a final thought to leave folks with. We've talked about achieving these really high gains with cascode amplifiers, often using a cascode load for the best case.
Right, the maximum possible gain setup.
But as you think about that, consider the practical side. What are the trade-offs of pushing for so much gain in just one single stage? How might other factors we haven't dived into, like power consumption or electronic noise, or just the physical chip area these larger transistors might take up, how might those things influence a real-world designer? Would they always choose this best-case high-gain cascode? Or might they sometimes opt for a simpler, maybe lower-gain alternative for other reasons? How do those decisions ultimately shape the performance and maybe even the limitations of the phones, computers, and gadgets you rely on every single day?
That's a great question. Because the best on paper isn't always the best in practice. There are always those system-level trade-offs to consider.